Hello, and today's lesson is about free fall. We know, the old adage, what goes up must come down. But in physics, we know that that is because of gravity. We are on planet Earth, and when we let something go, it tries to get pulled back towards the planet, towards Earth. As a matter of fact, any planet or moon or anything of considerable amount of mass is going to generate some gravity and try to pull other mass nearby. Why does that work? It's a little more complicated. You're going to have to go check out Einstein and some other things that are well beyond the scope of this course. But the point is that things fall towards the center of whatever planet you're standing on, if something falls, and those things generally fall at a constant acceleration. That acceleration depends upon what planet you're standing on, but things fall at the same rate of acceleration, which is a little wild because as Galileo Galilei discovered, all things, no matter how big or small they are, should fall towards the center of the planet at the same rate of that acceleration. Hold on one second. Sometimes that doesn't seem to make sense. I have a ball and a piece of paper, and when I drop them, obviously the ball fell much more quickly than did the paper. Well, that's because the paper ran into air resistance. But this rule of all things, no matter how big or small, falling at the same rate, in order for that rule to apply, it has to be an ideal situation where we remove air resistance. So there's nothing else holding us up as the objects try to fall. So I can take my paper and I can reduce the air resistance. It's the same paper, and it is still much lighter than a tennis ball. Even though they're two different objects of different masses, they should fall at the same rate. And pretty much they do if I let them go at the same time. And I don't think I quite did that, let them go at the same time. So I'll try it again. Here we go. Pretty good, right? Now, that means you can drop an SUV off the top of a building and a feather off the top of the building, and they should hit the ground at the same time. Again, but you have to remove air resistance. That means you'd have to remove the air, and that would be tough for the rest of us to breathe. So again, sometimes it's not so, it's harder to comprehend because we have air resistance a lot of the times in our everyday lives. On the planet Earth, that constant acceleration due to gravity is denoted as acceleration with a subscript g, acceleration due to gravity. And on Earth, that's a value of 9.81 meters per second squared. Some books in English units or British units will say 32.2 feet per second squared. We're not going to use that. But that acceleration is downward, always downward. So that acceleration, most likely, depending upon the way you have your what we call frame of reference, if positive is upwards motion, then acceleration downward is probably going to have a negative sign. And that's important because we're going to use this value in those acceleration formulas we just learned. Because we're moving at constant acceleration, those four acceleration formulas are absolutely valid. And a lot of the times we don't even use acceleration subscript g. Matter of fact, a lot of books will just use a lowercase g to replace the a in acceleration formulas. If you see that little g, you should automatically think acceleration due to gravity on Earth. On the moon, it's a little different. It's a different planet. It has a different acceleration on its surface when I drop things, when you drop things. If we were to be able to go to the moon, I don't think I'll ever get there, but maybe one day you will. Who knows? So acceleration due to gravity on the moon is about a sixth that of Earth. So it's about 1.62 meters per second squared. So I'm going to show you or I'm going to link one of the videos of astronauts on the moon dropping a feather and a hammer, showing you that they will drop at the same rate of acceleration. Because on the moon there is no air, so we don't have any air resistance to the feather, which is pretty neat. So check that out. What I'm going to do next, I need a minute to set up, is show you how to deal with this concept mathematically with the formulas, and also how we're going to deal with this with graphs, so with distance graphs and with velocity graphs. But it's very similar to what we've been doing, because it really is just another case of constant acceleration with a small twist. So, give me a minute.